chain Monte Carlo method. But it's expensive. You have to run it many, many times. And the samples will be correlated. And so it will take a little time. But in principle, you can, if you have a 4D var scheme, you can do it. And the way it works is that there's one way of defining such a dynamic process that has the right invariant distribution. Again, it comes from physics. It's Brownian dynamics. Brownian dynamics is a stochastic differential equation. Now, this is getting, again, a bit scary, but it's not too bad. So if you do data assimilation in the geosciences, you certainly, I hope you've seen ordinary differential equations. Of that form, so the change in Z is given by a right-hand side f, right? And we have numerical methods to solve this. It's Euler's method, right? Zn plus 1 is equal Zn plus a step size delta t times f at Zn. And Zn being an approximation to the solution at time Tn, Tn being equal to n times delta t, the step size. So you discretize your time domain with a step size of delta t, and then you find approximation to the exact solution by forward Euler's method. Right? You can actually, if I rewrite this, then you see that's nothing else than Zn plus 1 minus Zn divided by delta t equal to f of Zn. So this is an approximation to the derivative here, find a difference approximation forward, and the right-hand side you just evaluate where you are. So this method is very well understood. Now, here this SDE is a bit more complicated because we now add a noise term. So, and formally I can write this as a derivative. Of a time-dependent signal. Unfortunately, this is Brownian motion, Brownian motion, which is not differentiable. So we can't really write it this way. But we can go to the integral formulation and saying z at t plus tau minus z of t is equal to integral from t to tau, t plus tau f of z of s ds plus this thing evaluated at t plus, let me just, right. So you go to the integral formulation. I mean, you might remember that, you have differentiation and then you can always write it in integral form. And so, and that thing makes sense. For this type of noise I add here, and that noise is generated the following way. Again, I have my partition here in time. This is T1, T2, T3, etc. And this W is generated by starting at 0. And then I take a random jump that is distributed according to normal distribution with mean 0 and variance delta t. That gives me my first point. Then here I do the same again. I do from this point, I do a jump. I don't change the mean, so the mean is centered about this point, but I randomly jump with variance delta t. So I might go here, 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 up. And so then I can do linear interpolation, and that gives me an approximation to this W. So it's a random process that arises by randomly jumping with variance delta t, and delta t is the step size here. Right? Now this process, as you refine the grid, becomes infinite dimensional, and it's not differentiable. So it's continuous, but you can't differentiate. So that's why this doesn't make sense. Physicists still write it. It's all fine. You just need to know that you can't quite do it this way. And if you write it as an integral, it's fine, because then you're just comparing values at two different points of a continuous function. And so this is a stochastic process now, noise. And so I didn't write the integral, so I just write the d. So wherever you see a d, think of an integral, and then you back to that formulation. And my f is particular because the f is the log of the distribution. So it's basically your cost function of the negative of the cost function of 4d var. If you think of 4d var, this f, this expression is nothing else than the gradient of the cost function on 4d var. So you have to compute the adjoint and all this sort of stuff, but you can evaluate it. And then you can generate it. So the time t is, of course, not real time. So it's just a fictitious time. It's a computational time. So basically, 4d var, you take a trajectory, you compute the gradient of your cost functional. So that gives you an f. You add this to your previous trajectory. You add noise to it in this way, in each sort of, and then that gives you a new trajectory, and it's another sample from the distribution. So it's not just that you compute the minimum, but you sample the whole distribution. And one can show rigorously that this is sampling from the right distribution. I'm not going to go through this. It's a Fokker-Planck equation, but that's fine. And you have contraction principles and all that, so it works. And so numerically, now what I call n here is now an index I. So, but it's the Euler's method. So it's easy to implement. Again, this is just 4d var technology. You have to add noise to your trajectories in each point, and that gives you a new trajectory. Right? Now, if you're a strong Markov chain Monte Carlo person, then you will say, okay, I do a numerical approximation error here. So I might want to correct for it. I, as a numerical analysis person, believe you don't actually have to, because we have so many errors in the whole process involved. I mean, the model is not really clear. The likelihood, there are errors in the data. I mean, there's such a mess. There's no reason to exactly sample from this. So it can be a little time-stepping error. You can afford that. But if you want to, then you could do Metropolis Hastings, which basically means that you have another acceptance rejection criteria. So some samples being thrown away because they don't quite fit. But I personally, as I said, you don't have to do it. So in the hands, do you have actually 4d var for? Did you implement this 4d var for the Lorentz?
It's an exercise.
Oh, it's an exercise. Okay, so here's another exercise. So if you've done that exercise, then you can implement this and actually not only find the minimum, but actually sample from the whole distribution. Yeah?
I don't know too much about numerically solving SDs, but is Euler, Maruyama the best method available, or are there like higher order ones?
Okay, so this is a whole industry. That's a whole separate talk. So yeah, I didn't want to step into this, but I've been asked. So there's an issue. I mean, here it's not an issue because it's just a constant. There's an issue, how do you evaluate this integral? So there's Kratonovich, Ito, and all that sort of stuff. But here we don't need to worry about it. Euler-Maruyama is the lowest order method. There are better Mearstein methods, etc. So there's actually an industry, again, it comes out statistical physics and molecular dynamics and now also machine learning, how to fine-tune the stepping so that it preserves the invariant density to high precision. You don't need precision in the solution itself, but just in the preservation of this invariance. So yes, there's clever methods around. Yeah. They go also on the name of Hamiltonian Monte Carlo. Anyway, so now this is another method which is even simpler to implement. Because what you do, you say, okay, I want to evaluate this expectation value, but it's really hard to produce samples from desired distribution, which would be the posterior. So it's, let's say you don't want to evaluate gradients in 4D Wahl, right? You just don't like it. Then you can't use the method I just described. But you can still say, okay, I know the prior, which is normally just Gaussian. So I sample from this Gaussian. And then, of course, I have to then get the Radon-Nikodym derivative here, which is just a complicated way of saying here's the likelihood involved then, if it's Gaussian. And, but then you basically, these samples are from the wrong distribution, and you correct by it by giving them weights, importance weights. And the importance weights are the values of the likelihood or the Radon-Nikodym derivative at the sampled points. And that's it. But you don't have to take the prior. I mean, you can take anything else. I mean, if you have a cheap approximation of your posterior distribution somehow, you can use that. You just need to be able to compute the ratio of the two densities, the density you're proposing and the density you're targeting. That's the ratio you need to be able to compute. And again, they should sum up to m, et cetera, et cetera. And if it's space, then basically it's intuitive. If you were to do this for 4D Wahl, you would sample from the prior, which is Gaussian, easy to generate. Then you would compute the cost functional for that associated trajectory, and that's the weight. I mean, the cost function e to the minus. E to the minus, like the cost function. That would give you the weight. Problem again is that this can be potentially very small if you're in very high dimensions. So it won't work probably for 4D Wahl. I mean, the weights will be very tiny. A lot of the weights will be very small. And that has to do with what, again, there's an effective sample size behind. And the effective sample size is basically saying how many samples, if I could draw directly from the distribution independently, how many samples would I need to get the same statistical quality of my estimator. And there's this rho involved, which basically tells you you need to look into the variance of these weights. If the weights are all uniform, then it's perfect because the independent equally weighted, best estimator you can get. If the variance, if they all over the place, some small, some large, the variance is huge, then the effective sample size goes down, and it's not a good estimator. And you can estimate this quantity here, this ratio between your sample size and the effective sample size is an upper bound, is a Kullback-Leibler divergence. So, and again, that was a measure for the distance of two distributions. So if the distributions are too far away, then this method is not going to work well. And again, this is a curse of dimensionality, because this thing essentially blows up if you have a high-dimensional problem. So that quantity becomes very small. So important sampling in high dimensions, forget it. Right? And that's one of the reasons, again, why the field sort of this sequential Monte Carlo sort of was almost dying a couple of years ago, because people, okay, low dimensions, we know how to do it, fine, mostly done. But in high dimensions, it can't work because we have this curse of dimensionality. We know the effective sample size goes to 0 basically straight away, or very close to 0. It's not going to work. And then the ensemble-Kalman filter, again, is an intriguing way of getting around this. And localization, of course, right? And that sort of revitalized the whole discussion. OK, so this we already seen. And right, so now doing this specifically for data assimilation. So now we're looking at a particular form of the Bayesian inference problem. And what makes 4D Wahl, data assimilation in particular, because you have time, right? There's a sequential, very natural sequential way of thinking about it. And the sequential nature comes from the fact that the prior is generated through a dynamical system. So it's not like some big distribution somehow, but you can sort of go through it sequentially. And, you know, I mean, this is a sequential way of doing it. If you ignore this, then this can be your model. And in meteorology, I know you don't like stochastic perturbation somehow. In other fields, that's much more common and accepted because they know that these models have, you don't have so much confidence into the models. And so then you say, well, stochasticity is one way of accounting for model errors. So this can be a normally distributed random variable, but it can be something different. So here I chose it normal distributed with some prefactor q. You take the square root for reasons you will see later. And of course, you can also go back and say, okay, well, actually, we start with an ODE model, which is like the discretization, let's say, of the fluid equations. And then you want to account for model errors again. And if you want to do it in a continuous time way, you add this Brownian motion we already saw over there. And again, have a prefactor diffusion. And then you have a stochastic model, which then again, you can discretize by Euler's method. And then you essentially end up with something up here where this has a particular form. And here somehow there's a delta t involved. So from the discretization, you get a square root of delta t appearing up here. So easy to implement. That's what's generating the prior in a way. So the variable of interest is, if you look at, let's look at the window, is initial first and all the way to the end of the interval if you talk about discrete time. And you can also write down the joint distribution, the prior, recursively. So this is the distribution of your initial condition. And each of these things here gives rise to a transition probability. Basically, if you here, you know, you evaluate it, you apply the model, M, and then you add a Gaussian random variable to it. So this is a transition probability. So the transition probability is a Gaussian, centered about the output of your model for one step.